Hey everybody, in this video we're going to take a look at the idea of calculating a mantle potential temperature, the ideas behind it, and then we'll come back in another video and look at this spreadsheet Mantle TP calcs to see about the mechanics of doing so. So here we just want to explain what a mantle potential temperature is. The idea was really initiated by Cawthorne in 1975. He showed some of the essential calculations, but it was named and formalized by Mackenzie and Bickel in 1988. What they wanted to do was compare the temperature of the mantle that would be beneath, say, a mantle plume relative to ambient mantle. The idea is that a plume might be hotter than the mantle that surrounds it if you have a jet of upwelling material, as they put it, that was coming up from the core mantle boundary. And so that material having heat from the core mantle boundary might be hotter than ambient mantle, which would feed a mid-ocean ridge. So this TP here, what we call a plume, would be hotter than the mantle potential temperature here that would represent the mantle beneath the mid-ocean ridge. So what is that mantle? Their idea is that you take a parcel of mantle down here at some temperature that is below the mantle solidus. So if we're at a depth of about equivalent to 9 GPa pressure, we would be below the mantle solidus in temperature, so there would be no melting, it would be completely solid. And the potential temperature would be the temperature that that parcel of mantle would have if it could rise upwards along an adiabat without melting. And then what would be its temperature at the surface? And so the surface is our reference temperature, and that would be the potential temperature. The temperature, again, of a parcel of mantle if it could rise to the surface without melting. Now, of course, that does not happen. And if you do have a case of melting, then once this parcel of mantle hits the solidus, it's not going to follow that dashed line path here, but it's going to follow the solid line path here. This solid line represents the case, again outlined by Cawthorne in 1975, of the temperature path that you would obtain as solid is converted to melt. There's a certain amount of energy that's being consumed in turning solid to liquid, and so that's what causes the temperature to decline from the theoretical value here on the solid adiabat down to the actual value here during melting. Now, as this material rises upwards, it's generating more and more amounts of melt because it's higher above the solidus. The solidus is flatter than the adiabat, so the higher we rise up towards the surface, then the higher the adiabat is above the mantle solidus, and so the more melting we get, and so we have this much more significant cooling path. Now, if along that cooling path, somewhere along that path, melt is erupted, let's say, pools in the mantle at some point, and then is erupted straight up to the surface, that melt may record the temperature at which equilibration occurred. So we'd have this value here, the intersection on that horizontal axis, and then also with luck, we might be able to calculate the pressure at which equilibration occurred. So if we see some volcanic material that's been erupted here at the surface, hopefully we can reconstruct both the temperature and the depth at which it was equilibrated before it left the mantle. So that, if we come over here, the things that are in gray are our inputs. And then the blue are our outputs, which will follow the color scheme that we'll show in the CalcP iterative and input P spreadsheets when we get to that in another video. So from the melt composition, we are going to try to estimate the amount of melting occurred, the pressure at which the melt equilibrated in the mantle, the temperature at which equilibrated, and then we're going to assume that it's in equilibrium with olivine. So if there's no olivine in the mantle, this method will not work. If it is equilibrated with olivine, we're also going to calculate the olivine composition too. And so the melt composition is one of our key inputs. We need to know temperature and pressure because that's how we're going to recover that circle. We want to make correction for melting back up to the solid adiabat. Remember, what we want to do is follow this path here and find out this point here where that solid parcel would intersect the surface. So we have to first correct for the melting that occurs. That difference here is the temperature drop due to fusion. And to get that, we need to know F, the melt fraction. We also need to know the heat, the enthalpy of fusion, and then Cp is the heat capacity. And with this calculation here from Cawthorne, we can get that temperature drop. So if we add that temperature back in, now we can make another correction. That brings us, so if we get this liquid corrected back up to the adiabat, now we're sitting here. Now there's going to be a slight temperature drop due to the adiabat. The adiabatic calculation is shown here. That comes from work done in the middle of the 19th century. So for the mantle potential temperature, T sub P, it is Tm, the temperature of melting. That would be that circle there at some given pressure. Then we have the correction for the heat of fusion. So we're going to take that circle, correct it up to the solid adiabat. That's the correction there. And then we're going to follow that solid adiabat back up to the surface here. There's a little bit of cooling, and this is minus the pressure multiplied by this correction, T alpha V over Cp, where T is this temperature, the alpha is the thermal expansion coefficient, and Cp is, again, the heat capacity. V is the molar volume. It should really have a bar over it, but I didn't know how to do that in Excel, so we're just calling it a V. That is the volume of 1 mole of mantle material. So if you had 1 mole of mantle, how much space would it take up? What would be its volume? So that's it. Just for a quick review then, the mantle potential temperature is the temperature that a parcel of mantle would have if it could reach the surface without any melting or any conductive cooling. The way we're going to try to find it is use a melt composition as input. If there's a melt that's erupted at the surface, we're going to reconstruct the temperature and the depth at which it equilibrated in the mantle. We're going to estimate the melt fraction, and from the melt fraction and some known thermodynamic parameters, we're going to correct that melt composition. For the heat of fusion, we're going to correct the temperature back up to the solid adiabat, and then we're going to use the solid adiabat, again using other known thermodynamic parameters, to look at how much cooling would happen from our inferred depth to bring it back up to the surface. So it's that little bit of a circuit that gives us this mantle potential temperature here.